So in this class, I will explain how to compute the moment of inertia or second moment of area of an I section. Because normally in the civil engineering structures, T sections, I sections, they are all very important because in the design we will be having a beam, T beam, or in the case of steel structures, we can provide an ISMB section like that. So where the moment of inertia is a governing factor in the design. As I already told, as the value of moment of inertia increases, the strength of the member increases, and it can take more load. Fractional strength will increase because fractional strength is directly proportional to Young's modulus and moment of inertia. So therefore, computation of moment of inertia is a very important in the concept of analysis and design of structures. So here it is a VTU Model QP Problem. I section has been given. Determine for the I section shown. Number 1, moment of inertia about horizontal centroidal axis, moment of inertia about vertical centroidal axis, polar moment of inertia, and polar radius of gyration. And of course, the dimensions are given in millimeters. So here he has given the I section like this. The top flange has the dimensions 200 mm by 10 mm, bottom flange has the dimensions 300 mm by 10 mm, and the web portion. So this is the web portion. So you will learn this nomenclature when you study the analysis and design subjects. So this is called as top flange, this is called as bottom flange, and the middle portion is called as the web portion. So he has given all the dimensions in terms of millimeters. He has asked the moment of inertia about horizontal centroidal axis. That means we have to locate G for this I section. We know how to locate the centroid. So I have taken G here because normally centroid is closer to the region where the area is more concentrated. Here the top flange is having more area than the bottom flange is having more area than the top flange. Therefore, centroid normally lies near to the bottom flange where area is more. And I have taken the x-axis as the bottommost end, and if you observe the I section given, it is symmetrical about y-axis. So whatever left of y-axis is there, same thing is there to the right of y-axis. So therefore, it is symmetrical about the given I section is symmetrical about y-axis. I section is symmetrical about y-axis. So that means you need not calculate x bar here. So centroid G lies on y-axis. So that is the property. Centroid lies on y-axis. This is very important. Only we have to find out this y bar value. So once you get the y bar value, that is distance of the centroid from the assumed axis of reference x-axis. So using the formula, y bar is equal to summation ai yi divided by summation ai. We have used to locate the centroid. So you can locate that centroid, and then if you draw a axis which is horizontal passing through the centroid, that is dx axis. So we need to find now IGX here. So the first part we have to find out IGX, moment of inertia of the I section about the horizontal centroidal axis. Then we have to find out this IGY about vertical centroidal axis. Then we have to find out the polar moment of inertia IGZ, which is nothing but the sum of IGX and IGY by parallel perpendicular axis theorem according to definition of polar moment of inertia. And polar radius of gyration is kgz, which is given by kgx plus kgy, or not kgx plus kgy, it is nothing but root of igz by e, root of igz. So this is the formula to find polar radius of gyration. If they ask you to find radius of gyration about horizontal centroidal axis, then it is kgx. Kgx is equal to square root of igx by a, where a is the total area of the section, If they ask you to find polar moment of inertia about vertical centered axis KGY, it is IGY by A and W. So these are the formula we are going to use. Now first thing is to locate the centroid, that is to find the value of y bar. So to locate G, to locate the centroid G of this given section, for that what we do is, as you know how to locate the centroid of the composite section, we have to split this section into 3 rectangles, simple sections whose centroids can be located, easily located. So this is the given I section. So what I will do here is, I will take this as 1, this as 2, this as 3. So this can be split into 3 rectangles like this, whose centroids we can locate like this. So this is D1, this is D2, this is D3. So you know the dimensions. So the dimensions are given like this. This is 300 mm, this is 200 mm, this is also 300 mm, whereas this is 10 mm, this is also 10 mm, and width of web is also 10 mm. So these are the dimensions. Now x-axis I have taken here, y-axis I have taken here. This becomes the origin now. Now what I have to do is, I have to, as you know the procedure, I will write the values in the form of a table which I have used to locate the centroid to find x bar and y bar, as you know. So serial number 1, 2, 3, because there are 3 rectangles here. So for each rectangle we will write the values. So first one is the figure, second one is the area. Area is given, I will denote it as AI, whose dimensions are millimeter square, units is millimeter square. Then I need only yi value, because since it is symmetrical mode only y axis, only a yi value I need. Then the product ai yi, which will be in millimeter cube. Area is millimeter square, yi will be in millimeters, so millimeter cube. So these are the values I need to compute y bar. So let us do that. So here, first one is a rectangle. I have taken it as a rectangle. So it's a rectangle. Figure is a rectangle. Area is 300 into 10. 300 into 10, that is 3000 millimeter square. So second one is also a rectangle. So area of second rectangle is web piece I have taken as a rectangle. 10 into 300, that is also 3000. Then third one is also a rectangle whose area is 200 by 10. Third rectangle area is 200 into 10, that is 2000. So add this, you will get sigma ai. 3 plus 3 plus 2 is 8000. 8000 millimeter square is the value of sigma ai. Now yi is the distance of these centroids G1, G2, G3 from the x-axis. So that we have to write now. So G1 will lie at a distance of 10 divided by 2, that is 5 mm. This is 10 by 2 is equal to 5 mm. G2 will be at a distance of 10 plus half of 300. I will write here 10 plus 300 divided by 2, which is 10 plus 150, that is 160 mm. G3 will be at a distance of 10 plus 300, 4 and 10 plus 300, that is 310. 310 plus another 5, 10 divided by 2. So 310 plus 5, 315 mm. So this is the value of yi. Please note that all the centroids are above x-axis, therefore yi values are all positive. So now I have to take the product of these two. 3000 into 5, it comes out to be 15,000. 15,000 millimeter cube. Second one is 3000 into 160, which is 48 followed by 4 zeros. 1, 2, 3, 4. Be careful in the calculation. Then here 2000 multiplied by 315 means it is 630. 2 into 315 is 630 followed by 3 zeros. Yeah, these are the values. Now I will take sigma ai yi. Sigma ai will be in millimeter cube. So let us add all these three. So we will be getting 0, 0, 0 here. Then 0, 0, 5. Then 1 plus 8, 9. 9 plus 3, 12. 1 is remaining 11. I think it is 11 lakh 25,000. So 6.3 plus 4.8. So it comes out to be 11.1. 11.1 plus 0.15. Yeah, 11.25. So this is the sigma AI value. You do it carefully. Once again, you check it. This is 5. 1 plus 8, 9. 9 plus 3, 12, 1. Okay. Now, once you get the value of sigma AI, substitute here in this formula and get the value of y bar. 11 lakh 25,000 divided by sigma AI is 8,000. So if you divide that by that, you will get the value of y bar as. So these 3 zeros you can cancel. So 1125 divided by 8. 140.625. 140.625 millimeters. So this is the value of y bar. So this centroid will be now at a distance of 1. This is y bar. This y bar is 140.625. So this y bar is equal to 140.625 millimeters. So this is the first step, because we have to locate the centroidal axis. In order to locate centroidal axis, we need to locate the centroid, and then we have to draw horizontal vertical axis passing through that centroid G. Now, using parallaxis theorem, we have to evaluate the moment of inertia. So we have to use parallaxis theorem for that. According to parallaxis theorem, it states that if you want the moment of inertia of any area A, about an axis which is parallel to centroidal axis, and take centroidal axis, this is G and this is Gx axis, separated by a distance yc. Distance between these two parallaxes is yc. So these two are parallel. So if you want IAB, so IAB is equal to IGX plus A into yc square. So this is the parallaxis theorem which we are going to use here to compute the moment of inertia. So let us calculate now the moment of inertia about horizontal centroidal axis. Horizontal centroidal axis, which is nothing but IGX. So IGX I will write. So here IGX is nothing but I have to take the moment of inertia of the first one. So here what happens, please note that if I draw an axis passing through this G is here, this becomes your AB axis. Please be careful here. So this GX axis becomes the AB axis here. So whatever axis we are going to draw for each individual simple sections, they become the centroidal axis for the individual section. That means here I have shown for one figure there are 3 rectangles here. So what we have to do here is, now if at all I want this IGX becomes parallel to this G1x. It is like this. Let me show you, because this step is very important. In any problem of moment of inertia, we have to do like this. G is here, G1 will be here, G2 will be here, G3 will be here. So all these 3, they are lying on y-axis only, because it is symmetrical about y-axis. That is one advantage. And here if I draw an axis passing through this G, this is your IGX, and I can also draw an axis passing through this G1, that is G1x, an axis passing through this G2 is G2x, an axis passing through this D3 is D3x. Now here in this parallaxis theorem, IAB is nothing but IGX. Please note that, because all these are centroidal axis with respect to their own simple sections. I want this Gx axis now it is parallel to that. now. Only thing is I need these distances. These distances I need. Distance from G to G1, distance from G to G2, distance from G to G3. So these three distances I need. So this becomes your YC1, this becomes YC2, this becomes YC3, and your corresponding this area term becomes, this is A1, this is A2, this is A3. So those values I can get from here, from this table, which is used to compute the locate the centroid. Now these things once you apply, so you are going to get the value. So for each rectangle, for rectangle 1, rectangle 2, rectangle 3, we are writing this parallax theorem. This IGX is nothing but your IAB now is equal to IGX in this formula becomes IG1x about this. Suppose if I take this as AB axis, this as DX axis. So this is the area now I am going to consider. So that area is A1 I call into YC1 square. So please note that this is the moment of inertia of the first rectangle about the centroidal axis of the I section. Then for the second one it is IG2x. Similarly you can write plus A2 into YC2 square, plus for the third one it is IG3x plus A3 into YC3 square. Now we have to substitute the values now. So therefore IGX is equal to the first rectangle IG1x. So the moment of inertia of this rectangle about its centroidal axis is BD cube by 12. You know that it is BD cube by 12. Here it is B is 300, D is 10. So therefore it is 300 into 10 cube by 12 plus A1 is the area of this 300 into 10, that is 3000 multiplied by YC1. So now I need the distance YC1. YC1 is the distance from G to G1. So G is at the distance of. So from this, so this YC1 will be equal to, now I write here, YC1 is, this distance is this distance minus this distance. That means it is Y bar minus, so because from here to here it is 5, so Y bar minus 5 is the value of YC1. So Y bar is 140.625. 140.625 minus 5 is 135.625 mm. So your YC1 value is 135.625. So square of it. So this is for the first rectangle. Plus for the second rectangle, IG2x is BD cube by 12 of this rectangle. Please note that. So this rectangle BD cube by 12, this is 10. So this distance, this width of web is 10, and of course depth is 300, that is given. So 10 into 300 cube by 12. Be careful here. So BD cube by 12 for the second rectangle plus area of the second rectangle is also 3000. So 300 into 10, 3000 into YC2. Now YC2 is this value, distance from G to G2. So YC2 is equal to distance between these two centroids, G and G2. So then we can find out that this distance is now 10 plus 150, that is 160. Distance is 160. 160 minus y bar. So 160 minus y bar is the value of YC2, that is 160 minus 140.625, that is 19.375 mm. 19.375 mm. So 160, I just calculate, 160 minus 140.625, which is 19.375 mm. So this value is 19.375 square of plus for the third rectangle. For this is the third rectangle. So BD cube by 12 for the third rectangle is, this is 200 and this is 10. So 200 into 10 cube by 12, BD cube by 12 plus A3. So A3 is 2000, that is area of the rectangle. 200 into 10, 2000 into YC3. So YC3 square. So what is the value of YC3? Let us see. YC3 distance between G3 and G3 and G. For that, what we will do is this entire thing minus half of 10. Okay. So the entire thing is nothing but once again overall depth. Overall depth minus y bar. Overall depth of the I section is 300 plus 10 320. So 320 minus y bar, that is the distance from G to the stop head, From that I have to deduct this half of 10, which is minus 5. So it becomes 320 minus 140.625 minus 5. So this is what we get now. So that becomes 320 minus 145. I can take 145.625, which is 174.375. 174.375 mm. So that is the value of YC3, 174.375 square. So this is how we have to make use of parallel axis theorem. Once you simplify this, now you can get the value of IGX. Now let me write the value of IGX now. IGX is equal to, so we have to simplify all the three expressions. Be careful in the simplification. And then now let us write the value now. The first value. So IGX will be equal to, the simplification of this first term is 300 into 10 cube is 1000 divided by 12. Okay, plus 3000 into 135.625 square. The value now is 55207. 55207,421. 421.88 he has given. Okay, 0.88. So this is the first value. Be careful about the value because very big numbers you are getting. For the second term, 10 into 300 cube. So 10 into 300 cube divided by 12 plus 3000 into 19.375 square. So which comes out to be 23626. 23626. 171.88. This is the second value we got. Next the third value plus this is the third value. 200 into 10 cube. 200 into 10 cube is 1000 divided by 12 plus 2000 into 174.375 square. So that value is 60829. 60829 947.93. So be careful about these values, operate twice. So let me check once again using the calculator. 300 into 1000 divided by 12, the first value, plus 3000 into 135.625 square. That is the first value. 55207, 421.88. Okay. Second value, 10 into 300 cube divided by 12 plus 3000 into 19.375 square. It comes out to be 23626, 171.88. Correct. Then the third value, 200 into 1000 divided by 12 plus 2000 into 174.375 square. So it comes out to be 60829947.92. Correct. Now if you add these three, you are going to get the IGX value. Let us add all the three. 23626 171.88 plus 5520 7421.88. The value comes out to be 139,663,54 1.7 millimeter power 4. So this is the unit of moment of inertia. So 139,663,541.7. So this is the value of the moment of inertia about the horizontal centroidal axis. Once you get this about horizontal centroidal axis, now you can easily calculate this. We anyway have not asked for IGX. So let us go to moment of inertia about vertical centroidal axis IGY. So you should be very careful in the values because you are getting very huge values. So now we will calculate second part, that is moment of inertia about vertical centroidal axis. So we will calculate that. So let us see. So the value I will write down. Y bar is 140.625. IGX we got 139,663,541.7. So be careful about the values, very higher values we are getting. Now second part, we will calculate the moment of inertia about the second one. What we have asked is first one. Vertical centroidal axis, that is IGY. Here also we are using parallel system. So this is IGY. On similar lines we will write now IG1x, IG1y plus A1 into, now the distances are x distances. So for horizontal axis distances will be y, for vertical axis distances will be x. So A1 will be xe1 square plus for second rectangle IG2y plus A2 into xe2 square plus for the third rectangle IG3y plus A3 into xe3 square. Now here one important thing you can observe here xe1, xe2, xe3, they are all horizontal distances of these centroids G1, G2, G3 from the centroid G. So that is important. So here if you observe in the figure, since the figure given bisection is symmetrical about y-axis, the horizontal and all these are lying on y-axis itself. The horizontal distances between G1, G2, G3, they are all zeros because they are all lying on y-axis. So in this problem, xe1, xe2, xe3, all these three will be zero because the given figure, given I section is symmetrical about y-axis. This is very important. Any figure if it is symmetrical about x-axis, yc1, yc2, yc3 will be zero. Here, since it is symmetrical about y-axis, all these horizontal distances they become zero. That means this term becomes zero, this term becomes zero, this term becomes zero. Now you know that in the case of a rectangle, if you write the moment of inertia about the vertical centroidal axis, if this is B, this is D, so the formula to find IGY is dB cube by 12 or B cube D by 12. So this we have learned. For horizontal centroidal axis, BD cube by 12. For vertical centroidal axis, dB cube by 12. So now we will write that now for the first rectangle, IG1y for this rectangle, first rectangle, I have to use this formula now, dB cube by 12. That means 10 into 300 cube by 12. So please see the difference here. 10 into 300 cube by 12. That is the first rectangle. This term becomes 0. For the second rectangle, it is dB cube by 12 for this well proportion. This is second rectangle. So 300 into 10 cube. 300 into 10 cube by 12 for the second rectangle. Then for the third rectangle, it is dB cube by 12 for this. So which is nothing but 10 into 200 cube by 12. 10 into 200 cube by 12. So these three things if you add, you are going to get the moment of inertia about the vertical centered axis. Since 12 is common in the denominator, so what I can do here is this plus this plus this, entire thing divided by 12, I can make it out. So 10 into 300 cube. So 10 into 300 cube, that is the first value. Then plus 300 into 10 cube. 300 into 10 cube is 1000. That is second value. Then plus third value is 10 into 200 cube. That is the third value. Entire thing divided by 12 I will make. So which comes out to be 2919 1666 0.67. So this value is also in millimeter power 4. You can observe the value between and compare the values Igx and Igy. In this problem you can say Igx is very high compared to Igy. So here once again I will check the value 10 into 300 cube, okay, plus 10 into 300 cube plus 300 into 1000 into 300 cube plus 300 into 1000 plus 10 into 200 cube this entire thing divided by 2919 correct. So this is the value of moment of inertia of that I section about the vertical centroidal axis. Now here only thing is here you should know the difference between this YC1, YC2, YC3 and XC1, XC2, XC3. So if this section is symmetrical about y axis, all these x distances XC1, XC2, XC3 become 0 because all the centroids lie along the y axis and the horizontal distances between them will be 0. If any figure is symmetrical about x axis, then all the centroids lie along x axis and the vertical distance between the centroids will be 0, that is YC1, YC2, YC3 will be 0. Now the third part he has asked for the polar moment of inertia. Just if you add these two moments of inertia, you will get the polar moment of inertia according to perpendicular axis theorem. The polar moment of inertia Igz is given by Igx plus Igy. Now Igx is this value 1396635 41.7 plus Igy will be 29191666.67. So the value is 168,855 208.4 millimeter power 4. Just we have to add the value of Igx and Igy. Now the fourth thing is he has asked the polar radius of gyration. The polar radius of gyration is given by kgx. Polar radius of gyration kgx, according to the definition, it is kgz, which is nothing but Igz by A, and where A is the total area of that I section, which is nothing but sigma I, 3000 plus 2000, 8000. So that means now it is, I can write it as 168,855 208.4. This is Igx value, Igz value divided by total area is 8000. This is under root. So this is the value of polar radius of gyration. Whose unit is millimeters because I is in millimeter power 4, A is in millimeter square. Under root of millimeter square which is millimeters. Now I can just simplify this. So this it leads to the value now becomes 145.28. 145.28 mm is the polar radius of gyration. Suppose in the problem, if they ask you to find radius of gyration about the horizontal centered axis, then it is kgx. Please note, I have written here kgx, which is nothing but root of igx by a. Root of igx by a is kgx. So here igx we got 139663. 139663 541.7 divided by total area is as usual 8000. This is under root. So this you get it as 13963541.7 divided by 8000. So which is 17 point 139663,541.7 divided by 8000. This is under root 132.129. 132.129 under. Next, if you want the radius of gyration about the vertical centered axis kgy, which is given by root of igy by a. Root of igy by a. So here the last answer is igy we got 2919. So I can write here 2919 1666.67 divided by 8000 only. A is 8000 only under root. So this value, final value will be 29191666.67 divided by 8000 is equal to under root, comes out to be 60.41 millimeter. So this is the radius of gyration about vertical centered axis. So if they ask like this, we have to do that. Otherwise, if they ask only igx as a kgx, we can take root of igx by a. So this is how we have to do the problem on moment of inertia of an I section. But in the examination, whatever they ask, only those things you do. If they ask only moment of inertia about horizontal centered axis, you find only igx. If they ask about both or polar moment of inertia, then you have to find both igx and igy, and we have to add. If they ask radius of gyration, then only you do that radius of gyration using the respective formula.